We proved in class that, and this was the basic question that Turing started with, that there are numbers that are not computable, that they're uncomputable numbers. That was clear because the number of numbers was more than the number of Turing machines, right? That there must be some we can't compute. So what about the naturals? Is every natural number computable? Does our proof that there are some uncomputable numbers break? So it better break, otherwise the natural numbers would be uncomputable. So we proved that the reals included uncomputable numbers. And this is saying every natural number is computable. So why does that proof break? Well, there are more reals than there are naturals, right? That proof depended on the number of reals being uncountably infinite. Okay, so if we're going to prove that every natural number is computable, that's proving that for any natural number, there's some Turing machine that outputs that number, starting with a blank tape. Constructing one machine would not prove this. How are we going to prove this? Yeah. If we allowed anything on the input tape, we could start with an input tape that had any natural number on it. And then we don't have to do anything. The same notion that Turing had was this is a machine that starts with a blank tape and prints out the number. Definitely, if we could start with anything we want on the tape, we could start with different things on the tape that would add, but we don't even need to add to produce all the naturals. Okay, so we need to show that there's some machine, for any natural number, there's some machine that can print that number. Pretty close. Well, do we need to do anything that complicated? Binary representation is a bit of a pain. Let's use unary. So we could do it with binary. That would be complicated. But let's just do it like this. Machine K is going to be a machine that for K states, it's going to, for a blank on the input, it's going to write a 1, and it's going to move right. And it's going to have K states that do this, and it halts after the Kth state. Is that a valid proof? It's not one finite state machine. But for any K, the number of states is finite. And we know how to construct a machine that prints K once. Perfectly valid Turing machine. It's not a very interesting one. Definitely, you could do a more compact one. And if you were writing the numbers in binary, you could use less tape. But it's an infinite tape, so we don't need to conserve tape.